In the silence of the cosmos, where time itself feels infinite, the universe reveals a secret so staggering that it challenges every assumption we've ever held about existence. Imagine gazing into the night sky, a canvas of glittering stars. Galaxies painted like brushstrokes across the dark. At first glance, it seems eternal, serene, unchanging. Yet behind this stillness lies a motion so immense, so unstoppable, that it reshapes the very destiny of the cosmos. Galaxies are not simply floating islands of stars. They are rushing away from one another, like sparks flung from an invisible fire. Space itself is stretching, carrying entire clusters of galaxies apart in an endless cosmic drift. And with every passing moment, the universe grows larger, colder, and more mysterious. The further we look, the faster galaxies flee from us, as though some unseen hand is pushing them toward a distant horizon we cannot reach. But here's the unsettling truth. This movement is not slowing down under gravity's pull, as intuition would suggest. It is accelerating. Galaxies are not just drifting apart. They are racing away faster and faster, as though propelled by a force beyond our comprehension. A force we cannot see, cannot touch, yet one that governs the largest structures in existence. What is this force? Scientists have given it a name: dark energy. But a name is not an answer. It is a placeholder for the unknown, a symbol of how much we still do not understand. We measure its effects, we trace its fingerprints in the light of distant galaxies. But its true nature remains hidden in shadow. To understand the strangeness of this revelation, imagine for a moment how we once thought of the universe. For centuries, it was assumed that the cosmos was static, eternal, balanced in perfect stillness. The stars above were thought to be fixed, their patterns eternal. Even Einstein himself, when developing his theory of general relativity, resisted the idea of an expanding universe. He introduced a cosmological constant, a mathematical adjustment to hold the universe in place, because the alternative, a universe in motion, felt inconceivable. And yet, the universe defied him. It refused to stay still. The evidence, whispered through the faint redshifts of distant galaxies, and later shouted through the discovery of acceleration. What once seemed eternal and motionless was revealed to be alive, dynamic, restless. But here lies the paradox. If gravity is the great attractor, pulling matter inward, how can galaxies be flying apart with increasing speed? Gravity should bind the universe, slowing its expansion, eventually bringing it to a halt. Instead, the opposite occurs. Galaxies accelerate outward as though repelled by some invisible cosmic engine. This contradiction lies at the very heart of one of the greatest mysteries of modern physics. Some imagine this unseen force as the restless hum of the vacuum itself, a quantum energy infused in empty space. Others speculate about hidden fields, exotic particles, or new laws of physics waiting to be discovered. Still others wonder whether our very perception of space and time is incomplete, and that what we call expansion is but a shadow of a deeper truth. And yet, for all our theories, the mystery endures. The more we measure, the more the universe reveals its strangeness. Distant galaxies appear not merely as lights in the sky, but as messages from the past, carrying with them the story of cosmic acceleration. Their light stretches into the red, pulled by the expansion of space itself, reminding us that the cosmos is not a static backdrop, but a living, evolving reality. Here is the contrast that grips us. We, fragile beings on a small planet, are bound by gravity, by weight, by the constant pull toward the Earth. Yet on the largest scales, gravity's hold weakens, giving way to something more elusive, an unseen force strong enough to overpower the very glue of the cosmos. How can both be true? How can the force that binds us also yield to a deeper current that tears galaxies apart? The question is not only scientific but philosophical. It asks us to reconsider our place in the universe. If reality itself is governed by an invisible energy we cannot explain, what does that say about the limits of human knowledge? Are we explorers on the edge of a boundless frontier? Or are we forever imprisoned by the walls of our perception, capable only of naming mysteries, but never solving them? Every discovery carries with it both clarity and confusion. The expansion of the universe is a fact we can measure with astonishing precision. Yet the cause of that expansion remains one of the greatest riddles in all of science. Evidence and mystery, certainty and doubt. These opposites frame our search for truth. The unseen force tearing the universe apart does not just alter the fate of galaxies. It alters the fate of being itself. For if everything we know is accelerating into emptiness, then what is the destiny of life, of thought, of consciousness? Does the accelerating cosmos point toward inevitable dissolution, or does it hint at a deeper design we cannot yet grasp? In the end, the universe does not offer us answers. It offers us movement, silence, and mystery. The galaxies drift away, light fades into the void, and still we ask, why? Why is there something rather than nothing? Why does that something tear itself apart in ways we can barely comprehend? This is the mystery of dark energy, the invisible current of the cosmos. It is a scientific puzzle and a philosophical riddle, a force both real and unreal, present and unknowable. And it is here, in this collision between knowledge and ignorance, that the story of the universe truly begins. For as Einstein discovered, and as every physicist since has realized, the universe will not be confined to our expectations. It will expand beyond them. And so, we stand at the edge of comprehension, staring into the accelerating dark, knowing only this: the cosmos is in motion, and we are caught within its flow. What comes next is the story of how science first tried to tame this motion, and how it nearly blinded itself to the truth taught at the dawn of the 20th century. Physics stood at the edge of a revolution. Newton's laws had reigned for centuries, offering a simple and powerful vision: the universe as a clockwork machine, where every star and planet followed predictable paths under the invisible pull of gravity. For generations, this framework seemed unshakable. Yet in the mind of Albert Einstein, a quiet storm was forming, one that would redefine not only the laws of physics, but the very fabric of reality itself. Einstein imagined a cosmos, where gravity was not a mysterious force pulling at a distance, but a geometric truth woven into space and time. Instead of planets orbiting the sun because of some unseen tether, he saw them moving along the curved pathways of space-time itself, like marbles rolling across a warped sheet. Gravity, in this vision, was not an external power. It was the shape of the universe. General relativity, unveiled in 1915, was more than just a theory. It was a radical reimagining of existence. Space and time, once thought of as separate, became united in a four-dimensional fabric. Mass and energy told spacetime how to curve, and that curvature told objects how to move. With elegant mathematics, Einstein had written a symphony that explained the orbit of Mercury, the bending of starlight, and the dance of planets with a precision Newton could never have imagined. But Einstein's dream carried with it a hidden dilemma. His equations suggested a universe that could not sit still. The mathematics indicated that space-time itself should be dynamic, either expanding or contracting under the influence of gravity. And here lay the problem. Einstein, like most scientists of his time, believed in a static, eternal cosmos. The night sky seemed changeless, the stars eternal, and the very idea of a shifting universe felt unthinkable. Faced with this contradiction, Einstein made an extraordinary move. He added a new term to his equations, the cosmological constant, denoted by the Greek letter lambda. This subtle adjustment introduced a repulsive force into the fabric of spacetime, counteracting gravity's pull and holding the universe in balance. With this constant, Einstein's mathematics aligned once more with his intuition of a steady cosmos. Order was restored, at least for a time. The history would prove otherwise. In 1929, Edwin Hubble peered through his telescope and discovered something astonishing. Distant galaxies were not fixed. They were racing away from us. The light they emitted was stretched into longer, redder wavelengths, a cosmic signature of expansion. The universe was not static after all. It was alive with motion, rushing outward into the void. Einstein's carefully placed cosmological constant was no longer necessary. What he had added to save his equations became, in hindsight, a mistake. Legend has it that he later called it the biggest blunder of my life. The very term that had preserved his static vision now seemed like an unnecessary blemish on one of the greatest theories ever written. And yet, the story does not end there. Decades later, when scientists discovered that the universe's expansion was not merely continuing but accelerating, the cosmological constant resurfaced with renewed importance. What Einstein once dismissed as a blunder became central once again. Could lambda, this subtle repulsive energy embedded in spacetime, be the very key to explaining the mysterious force tearing the universe apart? This irony frames one of the great contrasts in science, the elegance of mathematical vision against the stubborn unpredictability of reality. Einstein's equations, when first written, pointed toward a dynamic universe, a truth he resisted because it conflicted with his philosophical belief in stability. The universe, however, does not bend to human preference. It bends only to its own laws, whether or not we are ready to see them. But even now, with all our modern discoveries, the cosmological constant remains a riddle. If it represents the energy of empty space itself, then why is its value so small? Quantum theory predicts a vacuum energy density so vast it would have torn the universe apart instantly. Yet observations show something incredibly gentle, subtle, almost balanced on a knife's edge. Why should the vacuum possess just enough energy to drive cosmic acceleration, and not infinitely more? Here lies the enduring puzzle. The mathematics is elegant, but the numbers make no sense. We can describe the phenomenon, but we cannot explain its true cause. Einstein's dream gave us the blueprint of a universe curved by gravity, but in doing so, it also opened the door to mysteries he never intended. The trouble with gravity, then, is not that it is wrong, but that it is incomplete. On the scales of planets, stars, and galaxies, Einstein's theory reigns supreme. Yet when we stretch our gaze to the largest scales of the cosmos, the theory falters. Something else is at work, an unseen actor woven into the expansion of the universe. Is it truly Einstein's lambda, resurrected from near oblivion? Or is it something far stranger, a force that lies beyond even the imagination of the man who redefined space and time? What makes this tale so compelling is the tension it reveals, between human certainty and cosmic indifference, between equations of perfect symmetry and a universe that refuses to conform. Einstein's vision was beautiful, almost poetic, yet reality itself proved far more unruly. The cosmos is not obliged to be elegant. It is obliged only to be what it is. Still, Einstein's work remains the foundation. General relativity has passed every experimental test with astonishing accuracy. From the bending of starlight during eclipses to the ripples of gravitational waves detected a century later. His equations are both a triumph and a tease, precise enough to guide us, incomplete enough to haunt us. The cosmological constant stands at the center of this tension, both a ghost of Einstein and a possible clue to the universe's deepest truth. Was it truly a blunder, or was it a flash of insight centuries ahead of its time? As we move forward in this story, We will see how the discovery of cosmic expansion forced physicists to confront the limitations of even the greatest minds. It showed that science advances not through certainty, but through error, correction, and the relentless dialogue between theory and observation. Einstein sought harmony in his equations, but the cosmos offered chaos. He dreamed of a static universe, but reality unfolded in motion. And now, as we grapple with the accelerating expansion of the universe, we return to the very symbol he once rejected, the cosmological constant, as a possible answer to the riddle of dark energy. The elegance of mathematics and the chaos of reality are locked in a timeless dance. And at the center of that dance lies a question that has haunted science for over a century. Is gravity truly understood, or is it merely the beginning of a deeper story? That deeper story begins with the man who confirmed the expansion itself, shattering the illusion of stillness and pointing humanity toward the restless truth of the cosmos. In the quiet hills of Southern California, in the 1920s, a lone telescope at Mount Wilson Observatory was pointed toward the heavens. Its 100-inch mirror, the largest in the world at the time, gathered faint whispers of starlight that had traveled for millions of years across the cosmic sea. At its eyepiece stood a man who would forever change our understanding of the universe. Edwin Hubble. Hubble was not the first to gaze at the galaxies, but he was the first to see what others had overlooked. The night sky had long been thought of as a map of stars bound to our own Milky Way. Nebulae, those faint smudges in the dark, were assumed to be nearby gas clouds, ornaments of our galactic home. But Hubble, patient and precise, studied them with determination. His work revealed a staggering truth. These nebulae were not part of the Milky Way at all. They were entire galaxies, immense islands of stars, millions of light years away. The universe was not just bigger than anyone imagined. It was unimaginably vast. This revelation alone would have secured Hubble's place in history, but it was only the beginning. By carefully studying the light from these galaxies, Hubble noticed something even stranger. The spectral lines of their light, the fingerprints of elements, were shifted toward the red end of the spectrum. This redshift was not random. It was systematic. The farther away a galaxy was, the more its light was stretched. At first, the implication seemed almost unthinkable. What could cause this cosmic redshift? One interpretation was Doppler motion. Galaxies moving away from us, their light stretched like the fading wail of a siren passing in the distance. But Hubble and his contemporaries soon realized it was not simply that galaxies were speeding through space. It was space itself that was expanding, carrying galaxies along with it like driftwood on a swelling tide. The cosmos was not static, eternal, and unchanging. It was dynamic, restless, and alive with motion. For centuries, science, and even philosophy, had assumed the opposite. From Aristotle to Newton, the dominant vision was of a universe fixed in place, eternal in its grand design. Even Einstein had resisted the notion of change, adjusting his own equations to preserve the illusion of stillness. The universe, it seemed, was too majestic to move, but the evidence was undeniable. Hubble's observations painted a picture of galaxies rushing apart, the fabric of the universe stretching in all directions. The universe was expanding. The reaction among scientists was one of astonishment, resistance, and eventual wonder. The revelation did not merely adjust a few numbers in existing theories. It shattered the very foundation of cosmology. A static cosmos meant permanence, a kind of cosmic certainty. An expanding cosmos meant beginning, change, and perhaps even an end. Imagine the intellectual whiplash of that moment. In one era, the universe was eternal, secure, almost comforting in its stillness. In the next, it became a story, a process, a narrative unfolding across billions of years. The cosmos was no longer a stage upon which events occurred. It was an actor itself, evolving, stretching, reshaping the destiny of everything within it. The contrast was stark. Certainty gave way to shock. Philosophy gave way to data. Belief in eternal stasis gave way to the unsettling evidence of expansion. But Hubble's discovery carried with it something even more profound. If the universe was expanding now, it must have been smaller in the past. Trace this logic backward, and you arrive at a singular point, a moment when the entire cosmos was compressed into an unimaginably dense beginning. This idea, later called the Big Bang, was radical, even controversial. Many resisted it, preferring instead to cling to the comfort of a universe without beginning. Yet the seed had been planted. Hubble's revelation pointed not only to expansion, but to origins, to the very birth of time and space. Still, the mystery was incomplete. Expansion explained the motion of galaxies, but it raised deeper questions. What was driving this cosmic stretching? Why was space itself inflating? And would it continue forever, or would gravity eventually slow it down? For decades, cosmologists wrestled with these questions, their debates reflecting the tension between evidence and interpretation. Some argued for a closed universe, destined to collapse back upon itself in a fiery end. Others envisioned an open universe, expanding endlessly into the void. And in the middle of these debates, the ghost of Einstein's cosmological constant lingered, a reminder that the equations of physics still held secrets yet to be uncovered. Hubble, in his modest way, was less interested in philosophical speculation and more in the data itself. He charted the galaxies, measured their redshifts, and mapped the expanding universe with the meticulous care of a cartographer of the unknown. His discoveries redefined cosmology, shifting it from abstract speculation to observational science. The universe was no longer a matter of belief. It was a matter of measurement. And yet, beneath the precision of numbers and graphs, there was wonder and perhaps unease. To think of galaxies racing apart, of space itself swelling larger with every passing second, was to confront the fragility of our place within it. We were no longer citizens of a fixed, eternal cosmos. We were travelers in a restless universe, caught in a current we could neither control nor fully understand. This shift did more than change science. It changed the meaning. A static cosmos carried the weight of permanence, a universe indifferent to time. An expanding cosmos carried the story of becoming, a universe with a past, a present, and a future yet unwritten. The human mind was forced to adapt, to reconcile itself with a reality far more dynamic and uncertain than tradition had allowed. Here, then, is the contrast that defines Hubble's legacy, the tension between what we once believed and what the universe revealed, between the comfort of stillness and the shock of motion, between a cosmos imagined and a cosmos measured.
But even as Hubble's data illuminated expansion, it concealed a deeper enigma. The galaxies were not only moving apart, they were doing so in defiance of gravity's pull. This would become the next great puzzle, one that would drag Einstein's abandoned cosmological constant back into the spotlight and give rise to a new, unsettling concept: dark energy. For if the universe was expanding, the real question was not simply how fast, but why. For centuries, the story of the universe seemed to move in a single direction: outward. Ever since Edwin Hubble first revealed in the 1920s that galaxies were drifting apart, astronomers assumed that the universe, like a stone thrown into the sky, was coasting away from its explosive beginning. Gravity, the eternal tug of matter, would one day slow that expansion. Perhaps it would bring everything to a halt, or maybe even drag the cosmos back into a final collapse. The universe's destiny, it seemed, was written in the equations. But then came the late 1990s when the universe refused to follow the script. Two rival teams of astronomers set out to measure the expansion of the universe with unprecedented precision. Their tool was one of the strangest gifts the cosmos provides: exploding stars. Type Ia supernovae, colossal detonations of dead white dwarfs, burn with such steady brilliance that they can be used as cosmic mile markers. By comparing how bright they appear from Earth to how bright they truly are, astronomers can measure the vast gulfs of space. They are the universe's lighthouses, guiding us across billions of light years. The expectation was simple. If gravity was tugging back on the cosmic fabric, then distant supernovae, relics of an earlier era, should appear brighter than expected. They should show us that the expansion was slowing down. Instead, the data delivered a shock. The supernovae were dimmer. The galaxies hosting them were not slowing in their retreat but racing away faster than before. The expansion of the universe was not decelerating. It was accelerating. It was as if a hidden hand had seized the cosmos and pressed the pedal to the floor. The implications were staggering. For the first time in human history, astronomers faced evidence that the universe was not only expanding but accelerating, as though driven by some invisible fuel. No known force in physics could explain it. Gravity pulls things together. Nothing in the equations suggested a natural push strong enough to counter it, let alone overpower it. And so a placeholder was born, dark energy. The name itself is a confession of ignorance. Dark not because it glows faintly or lurks in shadows, but because it lies beyond comprehension. Energy not because its nature is known, but because energy is the vaguest term in physics that still implies agency. It was, in truth, a linguistic lifeboat, a way to label a mystery too immense to leave unnamed. But I don't know. In giving it a title, humanity captured only the silhouette of a deeper truth. What is dark energy? A new substance? A flaw in our equations? A property of empty space itself? To this day, no one knows. It is a force without a face, a pressure without a source. Yet, according to current estimates, it dominates reality. Nearly 70% of the entire cosmos. Everything we see, stars, galaxies, nebulae, even the dark matter that binds them, is just a minority shareholder in existence. The true ruler of the universe is something we cannot see, cannot touch, cannot even properly describe. Pause for a moment and let that sink in. The stars overhead, the galaxies stretching across the night, all of cosmic history as we know it, is shaped by something that exists for us only as a question. This is where science collides with philosophy. In our search to understand the cosmos, we often mistake labels for comprehension. To name a mystery is to draw a boundary around it, to keep it safe within the pages of our equations. But naming does not resolve the unknown. It only reminds us of how much we do not know. The discovery of dark energy was more than just a revelation about the universe's future. It was a reminder of the limits of human knowledge. At the height of modern physics, armed with the most sophisticated telescopes and mathematical tools in history, scientists had encountered something so alien that it forced humility. The cosmos was not simply stranger than we imagined. It was stranger than we could imagine. Some likened it to Einstein's cosmological constant, an idea he had once inserted into his equations to balance the universe, and later dismissed as his greatest blunder. Could it be that Einstein's discarded term was, in fact, the very key to this mystery? If so, dark energy might be the quiet hum of empty space itself, the vacuum refusing to remain still, birthing expansion from nothingness. Others suggested it might be a new field of physics, a ghostly presence spread thin across the cosmos, subtle yet omnipotent. Still others whispered more radical ideas. Perhaps our understanding of gravity itself was incomplete. Maybe the equations that ruled the apple falling to Earth and the planets orbiting the sun did not fully apply when stretched across billions of light years. Each theory was both thrilling and unsatisfying, like trying to solve a riddle with missing words. The universe had revealed an answer, but the question remained hidden. And so, even as Nobel Prizes were awarded for the discovery, the mystery deepened. Scientists had pulled back the curtain, only to find a deeper shadow. Dark energy was not an explanation, it was an admission. But this is precisely what gives the discovery its power. It reminds us that science is not the conquest of truth, but the endless dialogue with mystery. Every solved equation opens new questions. Every frontier pushes us to confront the unknown. And in this case, the unknown is not marginal but central, the destiny of the entire cosmos. Because if the universe is accelerating, then its story will not end in collapse. The dream of a big crunch, a final rebirth of fire, is gone. Instead, the cosmos races toward a colder fate. Galaxies torn from view, stars burning out. The universe thinning into darkness as expansion continues without mercy. The night sky itself is being erased one star at a time. Imagine it, billions of years from now, astronomers on some distant world, if any remain, will look upward and see only blackness. No galaxies, no Milky Way, not even the faintest trace of what once was. They will be stranded in a cosmic solitude, unaware of the vastness we now glimpse. Dark energy is not just reshaping physics. It is rewriting the narrative of cosmic destiny. And yet, there is something hauntingly beautiful in this. For in discovering dark energy, we are reminded that the universe is alive with secrets. That reality is not a fixed script but a story unfolding with twists more profound than any myth. In naming the unknown, we glimpse both our own smallness and our extraordinary capacity to reach beyond it. Dark energy may never be fully understood. It may remain forever just beyond the horizon of human thought, a silence woven into the fabric of the cosmos. But perhaps that is the point. Perhaps the power of such mysteries lies not in solving them but in living with them, in allowing them to expand our sense of wonder. But even as Hubble's data illuminated expansion, it concealed a deeper enigma. The galaxies were not only moving apart, they were doing so in defiance of gravity's pull. This would become the next great puzzle, one that would drag Einstein's abandoned cosmological constant back into the spotlight and give rise to a new, unsettling concept: dark energy. For if the universe was expanding, the real question was not simply how fast, but why. For centuries, the story of the universe seemed to move in a single direction: outward. Ever since Edwin Hubble first revealed in the 1920s that galaxies were drifting apart, astronomers assumed that the universe, like a stone thrown into the sky, was coasting away from its explosive beginning. Gravity, the eternal tug of matter, would one day slow that expansion. Perhaps it would bring everything to a halt, or maybe even drag the cosmos back into a final collapse. The universe's destiny, it seemed, was written in the equations. But then came the late 1990s when the universe refused to follow the script. Two rival teams of astronomers set out to measure the expansion of the universe with unprecedented precision. Their tool was one of the strangest gifts the cosmos provides: exploding stars. Type Ia supernovae, colossal detonations of dead white dwarfs, burn with such steady brilliance that they can be used as cosmic mile markers. By comparing how bright they appear from Earth to how bright they truly are, astronomers can measure the vast gulfs of space. They are the universe's lighthouses, guiding us across billions of light years. The expectation was simple. If gravity was tugging back on the cosmic fabric, then distant supernovae, relics of an earlier era, should appear brighter than expected. They should show us that the expansion was slowing down. Instead, the data delivered a shock. The supernovae were dimmer. The galaxies hosting them were not slowing in their retreat but racing away faster than before. The expansion of the universe was not decelerating. It was accelerating. It was as if a hidden hand had seized the cosmos and pressed the pedal to the floor. The implications were staggering. For the first time in human history, astronomers faced evidence that the universe was not only expanding but accelerating, as though driven by some invisible fuel. No known force in physics could explain it. Gravity pulls things together. Nothing in the equations suggested a natural push strong enough to counter it, let alone overpower it. And so a placeholder was born: dark energy. The name itself is a confession of ignorance. Dark not because it glows faintly or lurks in shadows, but because it lies beyond comprehension. Energy not because its nature is known, but because energy is the vaguest term in physics that still implies agency. It was, in truth, a linguistic lifeboat, a way to label a mystery too immense to leave unnamed. But I don't know. In giving it a title, humanity captured only the silhouette of a deeper truth. What is dark energy? A new substance? A flaw in our equations? A property of empty space itself? To this day, no one knows. It is a force without a face, a pressure without a source. Yet, according to current estimates, it dominates reality. Nearly 70% of the entire cosmos. Everything we see, stars, galaxies, nebulae, even the dark matter that binds them, is just a minority shareholder in existence. The true ruler of the universe is something we cannot see, cannot touch, cannot even properly describe. Pause for a moment and let that sink in. The stars overhead, the galaxies stretching across the night, all of cosmic history as we know it, is shaped by something that exists for us only as a question. This is where science collides with philosophy. In our search to understand the cosmos, we often mistake labels for comprehension. To name a mystery is to draw a boundary around it, to keep it safe within the pages of our equations. But naming does not resolve the unknown. It only reminds us of how much we do not know. The discovery of dark energy was more than just a revelation about the universe's future. It was a reminder of the limits of human knowledge. At the height of modern physics, armed with the most sophisticated telescopes and mathematical tools in history, scientists had encountered something so alien that it forced humility. The cosmos was not simply stranger than we imagined. It was stranger than we could imagine. Some likened it to Einstein's cosmological constant, an idea he had once inserted into his equations to balance the universe, and later dismissed as his greatest blunder. Could it be that Einstein's discarded term was, in fact, the very key to this mystery? If so, dark energy might be the quiet hum of empty space itself, the vacuum refusing to remain still, birthing expansion from nothingness. Others suggested it might be a new field of physics, a ghostly presence spread thin across the cosmos, subtle yet omnipotent. Still others whispered more radical ideas. Perhaps our understanding of gravity itself was incomplete. Maybe the equations that ruled the apple falling to Earth and the planets orbiting the sun did not fully apply when stretched across billions of light-years. Each theory was both thrilling and unsatisfying, like trying to solve a riddle with missing words. The universe had revealed an answer, but the question remained hidden. And so, even as Nobel Prizes were awarded for the discovery, the mystery deepened. Scientists had pulled back the curtain, only to find a deeper shadow. Dark energy was not an explanation, it was an admission. But this is precisely what gives the discovery its power. It reminds us that science is not the conquest of truth, but the endless dialogue with mystery. Every solved equation opens new questions. Every frontier pushes us to confront the unknown. And in this case, the unknown is not marginal but central, the destiny of the entire cosmos. Because if the universe is accelerating, then its story will not end in collapse. The dream of a big crunch, a final rebirth of fire, is gone. Instead, the cosmos races toward a colder fate. Galaxies torn from view, stars burning out. The universe thinning into darkness as expansion continues without mercy. The night sky itself is being erased one star at a time. Imagine it, billions of years from now, astronomers on some distant world, if any remain, will look upward and see only blackness. No galaxies, no Milky Way, not even the faintest trace of what once was. They will be stranded in a cosmic solitude, unaware of the vastness we now glimpse. Dark energy is not just reshaping physics. It is rewriting the narrative of cosmic destiny. And yet, there is something hauntingly beautiful in this. For in discovering dark energy, we are reminded that the universe is alive with secrets, that reality is not a fixed script but a story unfolding with twists more profound than any myth. In naming the unknown, we glimpse both our own smallness and our extraordinary capacity to reach beyond it. Dark energy may never be fully understood. It may remain forever just beyond the horizon of human thought, a silence woven into the fabric of the cosmos. But perhaps that is the point. Perhaps the power of such mysteries lies not in solving them but in living with them, in allowing them to expand our sense of wonder. At first glance, a vacuum seems like nothing at all, pure emptiness, an eternal void. But in quantum mechanics, even nothing is alive. The uncertainty principle tells us that particles flicker in and out of existence, like fireflies flashing in the night. These quantum fluctuations, tiny but incessant, give the vacuum a restless energy. This vacuum energy, though invisible, may permeate every inch of the universe. And if it does, it could be the force that accelerates cosmic expansion, a steady pressure inflating reality itself. It is a haunting idea that nothingness is not truly nothing, but a seething ocean of energy. If true, then the universe is carried forward not by matter or motion, but by emptiness itself. Here lies the static vision, unchanging, ever-present, woven into the laws of quantum physics. It is elegant, it is grounded, and yet it poses a disturbing problem. When physicists attempt to calculate the actual amount of vacuum energy predicted by quantum theory, the result is catastrophic. The equations suggest a value so enormous that it would rip the universe apart in an instant. And yet, the measured energy, the so-called cosmological constant, is far smaller, almost unimaginably so. The mismatch between theory and reality is not a minor error. It is one of the greatest discrepancies in all of science, a mismatch of over 120 orders of magnitude. This vacuum catastrophe leaves a wound in our understanding. If quantum physics is correct, why does the vacuum not destroy us? Why does the universe feel tuned, almost deliberately, to a delicate balance? It is here, in the cracks of certainty, that another vision steps forward, one less grounded in physics, and more open to the unknown. This vision is quintessence. Unlike vacuum energy, quintessence is not static. It is dynamic, alive, and evolving. Imagine a cosmic field stretching across the universe, invisible yet present everywhere. Unlike the cosmological constant, which simply is, quintessence shifts over time, waxing and waning like the tides. It is not empty space itself, but a mysterious force that behaves almost like a new form of matter, except it refuses to clump or collapse. Instead, it spreads out evenly, influencing the expansion of the universe from the shadows. The idea of quintessence resurrects something ancient. In Greek philosophy, quinta essentia, the fifth essence, was the divine substance believed to fill the heavens, beyond the four earthly elements. To invoke quintessence today is to suggest that the universe may indeed be pervaded by something we cannot see, cannot touch, but may one day measure. A field that is not fixed in stone, but fluid, restless, responsive. Where vacuum energy whispers of inevitability, quintessence hints at possibility. This dynamic quality carries profound implications. If quintessence changes with time, then the fate of the universe is not sealed. Vacuum energy, steady and eternal, would doom the cosmos to endless acceleration, galaxies receding into cold isolation, stars burning out, and space stretching into silence. But quintessence could change course. It might weaken, allowing gravity to reassert itself. It might strengthen, tearing the cosmos apart in a final big rip. Or it might oscillate, guiding the universe through cycles of growth and decay. Where vacuum energy locks us into destiny, quintessence opens the door to an unfinished story. This is more than a scientific puzzle. It is a philosophical confrontation. On one side lies the security of established physics, even if its equations misfire. On the other, the willingness to speculate, to imagine forces beyond what is yet proven. Do we trust the solidity of quantum theory, or dare to embrace the uncertainty of invention? Are we explorers of the known, or pilgrims of the unknown? Physicists find themselves divided. Some cling to vacuum energy, convinced that the mismatch between prediction and reality is simply a matter of missing pieces in mathematics. Others pursue quintessence, inspired by the thought that our universe may still harbor undiscovered laws, hidden dimensions, or exotic fields that transcend today's understanding. The debate is not polite. It is fierce. Each side accuses the other of blindness. To the champions of vacuum energy, quintessence is little more than fantasy, an unnecessary invention. To the advocates of quintessence, vacuum energy is an incomplete story, a theory that collapses under its own contradictions. And yet, beneath the arguments, one truth remains. We do not know. Our instruments measure the acceleration of the cosmos, but they do not reveal the engine behind it. The evidence is a shadow, a whisper, We are left to choose between two mysteries, neither fully satisfying, each carrying its own weight of doubt. But perhaps the choice is not so simple. Perhaps vacuum energy and quintessence are not rivals, but layers of a deeper reality. Could the quantum fluctuations of the vacuum coexist with a larger, evolving field? Could quintessence be born out of the very uncertainty that defines the vacuum? These questions blur the line between physics and metaphysics, between science and story. The answers, if they come, will not only reshape our equations but our philosophy of existence. For in the end, this debate touches more than cosmology, it touches meaning itself. If vacuum energy is real, then we live in a universe ruled by inevitability. Its acceleration is not a choice but a decree, written into the very nothingness of space. We are passengers on a one-way journey into silence. But if quintessence is true, then the cosmos is alive with possibility, shifting and changing like a great organism. We may live not in a finished universe, but in a universe still becoming. The stage is set, vacuum energy, the static ghost of quantum law, against quintessence, the evolving shadow of speculation. Both seek to answer the same haunting question, yet both leave us staring into uncertainty. We stand at the edge of knowledge, peering into darkness, guided only by faint glimmers of light. What lies beyond remains unseen. But the debate itself, the tension between physics and philosophy, evidence and imagination, is the heartbeat of discovery. For now, we do not know whether nothingness drives the universe forward, or whether a hidden essence shapes its destiny. All we know is that the cosmos continues to expand, indifferent to our theories, patient as we struggle to keep pace with its secrets. And so, the mystery deepens. From the quantum whisper of the vacuum to the speculative breath of quintessence, the universe confronts us with a riddle that refuses to be solved. It is a riddle not only of physics but of existence, of what it means to live in a reality we cannot fully comprehend. As we move forward, the debate will sharpen, and new evidence may rise from the heavens themselves. But for now, we stand between two visions of the infinite, caught between the certainty of the known and the seduction of the unknown. The universe, at first glance, appears to be a seamless fabric, vast, smooth, and governed by elegant equations. Yet, when we look closely, cracks begin to appear. These cracks are not physical tears in space, but tensions in the numbers, whispers that the story we tell ourselves about the cosmos may not be complete. Take the Hubble tension. For a century, we've measured how fast the universe is expanding. The answer should be the same no matter how we measure it. But it isn't. Local measurements from nearby stars and galaxies give one rate. Observations of the early universe, encoded in the cosmic microwave background, give another. Two rulers, both precise, yet their results do not agree. It's like measuring the same bridge with two different instruments and finding it longer in one direction than the other. Then there is cosmic anisotropy, the unsettling idea that the universe may not look the same in every direction. For decades, we believed in the cosmological principle, that the cosmos is homogeneous and isotropic, no matter where or how you look. Yet some data suggest a faint axis, a cosmic preferred direction, as though the universe itself has an orientation. If true, it would shatter one of the most sacred assumptions of cosmology. And what of dark energy? 68% of the universe, yet invisible, untouchable, and inferred only through mathematics. What if it isn't real at all? What if the accelerated expansion we see is not evidence of a mysterious energy, but of something else we've misunderstood? A flaw in our models, a blind spot in our reasoning. Here lies the paradox. Science thrives on precision, yet precision itself has revealed inconsistencies. The more clearly we see, the less the picture holds together. Each observation adds weight to our knowledge but also deepens the shadows of our doubt. Is the universe expanding faster than expected? Or are we misreading the signs? Does the cosmos stretch in every direction equally? Or are we caught in a grand illusion of symmetry? Are we measuring dark energy, or only the limits of our imagination? The cracks in the cosmic fabric are not signs of failure, but of possibility. They tell us the story is not finished, that reality may be stranger than even our most daring theories allow. And as we turn to the next chapter, we confront an even deeper question. If the universe resists our attempts to pin it down, what does that say about the very act of measurement, and the mind that seeks to measure it? Time is not infinite, not even for the universe. In the depths of space, where galaxies drift like dying embers against the cosmic dark, a countdown has already begun, not measured in seconds or years, but in epochs so vast they dwarf human comprehension. The phantom force we call dark energy, that invisible hand pushing the cosmos apart, has sealed the universe's fate. And that fate is written in 3 possible endings, each more haunting than the last. Picture the night sky as it appears now. Stars scattered like diamonds, the Milky Way stretching across the heavens, distant galaxies glowing with the light of billions of suns. This vista, which has inspired poets and philosophers for millennia, is temporary, a fleeting moment in cosmic history. The expanding universe is already erasing it, pixel by pixel, star by star. The first scenario is the big freeze, cosmic winter without end. As dark energy continues its relentless push, galaxies will drift beyond the horizon of visibility. One by one, they will vanish from view, their light stretched so thin that it fades into nothingness. Our own galaxy will become an island in an ocean of black, isolated and alone. The stars around us will burn through their nuclear fuel and die. Red dwarfs will glow for trillions of years, but even they will eventually exhale their last breath of light. The universe will grow cold, dark, and empty, a graveyard of burnt-out stellar corpses floating in an ever-expanding void. But perhaps that mercy is too kind. The second possibility is heat death, not the flame of destruction, but the silence of equilibrium. In this scenario, the universe reaches a state of maximum entropy, where all energy is evenly distributed and no work can be done. Stars still die, black holes still evaporate through Hawking radiation, but the process stretches across incomprehensible timescales. Eventually, even black holes, those final bastions of cosmic structure, will decay into elementary particles. The universe becomes a thin soup of photons and leptons, spread so thinly that particles rarely interact. It is death by dispersal, existence diluted into meaninglessness. Yet there is a third path, more violent than either, the Big Rip. If dark energy is not constant but grows stronger over time, if it is quintessence in its most aggressive form, then the phantom force will eventually overcome not just gravity on cosmic scales, but every force that holds matter together. First, galaxy clusters will be torn apart. Then individual galaxies will dissolve, their stars scattered like dust in a hurricane. Solar systems will disintegrate as dark energy overwhelms the gravitational bonds that keep planets in orbit. Finally, in the ultimate act of cosmic vandalism, dark energy will grow so powerful that it rips apart molecules, atoms, and even subatomic particles themselves. The universe will not fade quietly into darkness. It will be shredded into its most fundamental components, leaving behind only empty space expanding at an exponential rate. The contrast is stark and unsettling. Here we stand, biological beings who have existed for the briefest flicker in cosmic time, contemplating the eternal silence that awaits. Our species has walked this planet for perhaps 300,000 years. Recorded history spans a mere 5,000 years. The entire story of human civilization, from the first cave paintings to the launch of space telescopes, occupies less time than it takes light to travel from one edge of our galaxy to the other. And yet, in this infinitesimal moment of existence, we have learned to read the universe's death certificate. There is something both magnificent and tragic in this revelation. We are creatures of flesh and blood, bound to a single world, living for decades in a cosmos that will endure for trillions upon trillions of years. We are temporary arrangements of atoms in a universe that is slowly, inexorably, pulling itself apart. The very force that gave birth to galaxies, that allowed stars to shine and planets to form, that created the conditions for life itself, will ultimately undo all of it. But perhaps this is precisely what gives meaning to our brief time here. In a universe destined for emptiness, consciousness becomes precious beyond measure. We are the cosmos reflecting upon itself, the universe awakening to its own story. For a fleeting moment in the vast sweep of cosmic time, matter has organized itself into patterns capable of wonder, love, creativity, and understanding. We are not just witnesses to the cosmic drama, we are participants in it. The phantom force that drives dark energy may be pushing us toward inevitable doom, but it is also the same energy that shapes the space in which we exist. Without it, the universe might have collapsed back upon itself eons ago, never giving stars enough time to forge the heavy elements that make planets and life possible. In a strange sense, our existence and our ultimate extinction are written by the same invisible hand. This is the paradox of cosmic perspective. The universe's indifference to human life makes human life more precious, not less. The brevity of our moment makes it more urgent to love, to discover, to create, to understand. We live not despite the phantom force, but because of it, temporary patterns of complexity in an ocean of expanding space. As dark energy continues its quiet work, stretching space and dimming the stars, we are left with a choice. We can despair at the cosmic loneliness ahead, or we can marvel at the extraordinary improbability of our existence. We can mourn the death of the universe, or we can celebrate the brief, brilliant flowering of consciousness that allows us to contemplate such vast timescales at all. The phantom force is real. The cosmic doom it promises is inevitable. But between now and that unimaginably distant future lies the entire story of what we might become. In the face of universal entropy, we persist. In the shadow of cosmic death, we create meaning. In the presence of dark energy, we choose to burn brightly while we can. The universe may be heading toward silence, but for now, it hums with the sound of minds awakening to their own mortality, and finding in that awakening not despair, but a deeper appreciation for the miraculous accident of being alive in a cosmos vast beyond imagining. What if the largest mystery in the universe hides in the smallest places? While galaxies race apart under dark energy's invisible grip, another drama unfolds at a scale so minute it defies imagination. In the quantum realm, where particles flicker in and out of existence, where empty space seethes with hidden energy, where the very act of observation changes reality, lies a secret that might hold the key to cosmic expansion itself. The quantum world is a place where common sense dies. Here, particles exist in multiple states simultaneously until forced to choose. Here, pairs of particles spring from nothingness, dance briefly in existence, then vanish back into the void. Here, the vacuum of space is not empty but alive, a restless ocean of potential energy that refuses to remain still. This quantum vacuum energy may sound like science fiction, but it is as real as the ground beneath your feet. The Casimir effect proves it. Place two metal plates close together in a vacuum, and they will be pushed together by the very nothingness between them. The space around the plates contains less quantum energy than the space beyond, creating an imbalance that generates measurable force. Empty space has pressure. Nothingness pushes. Could this be the answer to dark energy? The idea is seductive. If quantum fluctuations permeate every cubic centimeter of space, their accumulated energy might provide the gentle push that accelerates cosmic expansion. The vacuum itself becomes the engine, its quantum restlessness the fuel that drives galaxies apart. It would be elegant, even poetic, the smallest phenomena governing the largest structures, the microscopic dictating the cosmic. But elegance and reality are not always friends. When physicists attempt to calculate the actual energy density of the quantum vacuum, the numbers become catastrophic. According to quantum field theory, empty space should contain so much energy that it would curl the universe into a ball smaller than a proton. The predicted vacuum energy density exceeds observations by a factor of 10 to the power of 120, a number so large it has more zeros than there are atoms in the observable universe. This is the vacuum catastrophe, one of the most spectacular failures in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or something cancels out almost all of the vacuum energy, leaving behind only the tiny residue we observe as dark energy. The precision required for such cancellation is mind-boggling, like balancing a pencil on its point while blindfolded in an earthquake. Yet the quantum realm offers other mysteries that might illuminate the cosmic puzzle. Consider virtual particles, those ghostly figures that emerge from the quantum foam and disappear before they can be detected. They violate energy conservation for brief moments, borrowing existence from the future and paying it back before the universe notices. These quantum loans happen everywhere, all the time, in every empty inch of space. They are not real in the traditional sense, yet their effects are measurable. They alter the energy levels of atoms, they contribute to forces between particles, they make the vacuum a dynamic, ever-shifting tapestry of potential. Some theorists wonder, could these virtual particles, in their collective restlessness, generate a kind of quantum pressure that pushes space apart? Not through their energy, which appears and vanishes too quickly to accumulate, but through their very existence as fluctuations in the fabric of spacetime itself. The idea ventures into speculative territory, but so did quantum mechanics once. The history of physics is littered with impossible ideas that later became cornerstones of reality. Wave-particle duality seemed absurd until experiments forced acceptance. Quantum entanglement was dismissed as spooky action at a distance, until it became the foundation for quantum computing. Perhaps the connection between quantum fluctuations and cosmic expansion awaits its own moment of recognition. There is something profound in this potential link between the infinitesimal and the infinite. On one scale, quantum fields create particles from nothingness in spaces smaller than atomic nuclei. On another scale, dark energy stretches the fabric of spacetime across billions of light-years. The contrast in scale is staggering, like comparing the period at the end of this sentence to the diameter of Earth. Yet both phenomena share a common thread. They emerge from the fundamental structure of space itself. This connection hints at a deeper unity in physics, a hidden symmetry that bridges the quantum and the cosmic. If the restless energy of the vacuum drives the expansion of the universe, then every empty point in space becomes an active participant in cosmic evolution. The void between atoms in your body would be connected to the void between galaxies in the observable universe. You would literally carry within yourself the same force that shapes the cosmos. But the mystery deepens when we consider quantum fields themselves. In quantum field theory, particles are not tiny billiard balls but excitations in underlying fields that permeate all of space. The electron is an excitation in the electron field, the photon an excitation in the electromagnetic field. Even when no particles are present, these fields remain, humming with zero-point energy, the minimum energy they cannot lose even at absolute zero temperature. This zero-point energy is not just theoretical. It has measurable effects on atomic spectra, it influences chemical reactions, it even affects the behavior of superconductors. The quantum fields are real, their energy is real, and their presence fills every corner of the universe. If dark energy emerges from these fields, then the expansion of space is driven by the very foundation of matter and energy themselves. Yet questions multiply faster than answers. Why would quantum field energy suddenly begin dominating cosmic evolution only in recent epochs? For billions of years after the Big Bang, matter and radiation controlled the universe's expansion. Dark energy became significant only when the cosmos was already mature, galaxies formed, and matter diluted by expansion. What changed? What awakened the sleeping energy of the vacuum? Some propose that the quantum fields themselves evolve, their properties shifting as the universe expands and cools. Others suggest that dark energy is not quantum vacuum energy at all, but a new type of field with quantum properties. A dynamic entity that grows stronger as space stretches, feeding on expansion itself. The contrast between certainty and speculation becomes stark here. Quantum mechanics is among the most precisely tested theories in science, its predictions verified to extraordinary accuracy. Yet, when applied to cosmology, it produces results so wrong they seem almost comical. The quantum world we understand in laboratories becomes alien when extrapolated to cosmic scales. This tension reflects a deeper issue in modern physics: the inability to unify quantum mechanics with general relativity. Both theories work magnificently within their domains, but they speak different languages, follow different rules, make incompatible assumptions about the nature of reality. Dark energy sits precisely at their intersection, a phenomenon that might emerge from quantum processes yet manifests on gravitational scales. Perhaps the answer requires a new physics, a theory that transcends both quantum mechanics and general relativity. Such a theory might reveal that the quantum vacuum and cosmic expansion are two faces of the same phenomenon, two perspectives on a deeper reality that operates according to principles we have not yet discovered. Or perhaps the answer is simpler, hidden in plain sight within the mathematics we already possess. Sometimes the most profound truths wear the disguise of the mundane, waiting for the right perspective to reveal their significance. What remains certain is that the quantum realm refuses to be ignored in discussions of cosmic fate. Whether through vacuum energy, virtual particles, or quantum fields, the smallest scales of physics cast long shadows across the largest scales of the universe. The restless energy that animates atoms might be the same force that dims the stars. In the end, the quantum mysteries do more than offer possible explanations for dark energy. They remind us that reality operates according to principles that challenge every intuitive assumption about existence. At the deepest levels, the universe is not solid, predictable, or even classical. It is probabilistic, uncertain, and thoroughly quantum. If dark energy emerges from this quantum foundation, then cosmic expansion becomes not just a gravitational phenomenon but a manifestation of the fundamental strangeness of reality itself. The universe expands because, at its core, it is governed by uncertainty, probability, and the relentless creativity of the quantum void. The microscopic and the cosmic dance together in a partnership we are only beginning to understand. And in that dance lies both the mystery of dark energy and perhaps the key to unlocking the deepest secrets of existence itself. What if the universe is not just observed by consciousness but shaped by it? Standing at the intersection of quantum mechanics and cosmology, we encounter a question that makes even the boldest physicists uncomfortable. The expanding cosmos, driven by dark energy's invisible hand, may be more than a mechanical process unfolding in empty space. It may be intimately connected to the very act of observation, measurement, and conscious awareness itself. This is where science meets its own philosophical shadows. In quantum mechanics, the role of the observer is undeniable and unsettling. Particles exist in superposition, multiple states simultaneously, until the moment of measurement collapses them into definite outcomes. The famous double-slit experiment demonstrates this with chilling clarity. Electrons behave as waves when unobserved, as particles when watched. The universe, it seems, changes its behavior based on whether consciousness is paying attention. But if consciousness plays a role in determining the quantum properties of matter and energy, what role might it play in the expansion of space itself? The question sounds absurd to materialist science. The dominant view treats consciousness as an emergent property of complex neural networks, a byproduct of chemistry and electricity, impressive but fundamentally irrelevant to cosmic processes. In this framework, dark energy operates according to impersonal physical laws, indifferent to whether any conscious beings exist to observe it. The universe expands because quantum fields or cosmic constants dictate it, not because minds are present to witness the process. Yet the quantum world refuses to respect such tidy boundaries between observer and observed. Consider Wheeler's delayed choice experiment, which suggests that decisions made by observers in the present can retroactively determine the behavior of photons in the past. Or quantum entanglement, where the measurement of one particle instantly affects its partner across vast distances, seemingly violating the speed of light. These phenomena hint at a universe where consciousness and physical reality are more deeply intertwined than classical physics ever imagined. If the quantum vacuum energy that might drive cosmic expansion is subject to observer effects, then every conscious measurement of the universe's expansion rate becomes an active participation in that expansion. We are not just passive witnesses to cosmic acceleration, we are co-creators of it. This perspective leads to even stranger possibilities. What if dark energy is not a property of space but a property of observation itself? What if the act of conscious beings measuring cosmic distances and expansion rates creates the very phenomenon we are trying to understand? The universe might be expanding because conscious observers expect it to expand, their measurements collapsing cosmic superposition states into accelerating realities. The idea echoes ancient philosophical traditions that saw consciousness and cosmos as intimately connected. In Hindu cosmology, the universe is Brahman dreaming itself into existence. In Buddhist thought, mind and matter arise together in dependent co-origination. These traditions, dismissed by modern science as primitive superstition, may contain insights that quantum mechanics is only beginning to rediscover. But we must distinguish between speculation and evidence. The connection between consciousness and cosmic expansion remains highly speculative, lacking the rigorous experimental foundation that defines legitimate science. The quantum measurement problem, how and why observation collapses wave functions, is itself unresolved after a century of debate. Extending these mysteries to cosmic scales multiplies uncertainties rather than resolving them. Yet the questions persist because they touch something fundamental about the nature of existence itself. Consider the anthropic principle, the observation that the universe's physical constants seem fine-tuned for the emergence of complexity and consciousness. Dark energy's strength falls within the narrow range that allows galaxies to form while preventing immediate cosmic collapse or expansion so rapid that structure never develops. Too much dark energy, and the cosmos would have torn itself apart before stars could ignite. Too little, and gravity would have crushed everything back into a singularity.